how the world's electricity really reaches your home. Every time you flip a switch, a light turns on almost instantly. No delay, no warning, no visible effort. But what you are about to hear is one of the most complex and fragile systems that keeps modern life alive. If you enjoy understanding how the world really works, subscribe to the channel and turn on notifications. Every week, we reveal the hidden systems you depend on every single day. Electricity does not magically appear in your home. It travels through a vast invisible network that operates continuously, second after second, day after day. Most people never see it. Most people never think about it until it stops. Today, we are going to follow electricity from its origin all the way to your light switch. Cities do not rely on a single power source. They combine hydroelectric dams, coal and gas plants, nuclear reactors, solar farms, and wind turbines. Each source is carefully monitored. Power output, fuel availability, weather conditions, equipment status. If one source fails, the others must compensate immediately, because cities cannot pause. But the electricity collected at power plants is not ready to travel long distances. This is known as generated power. Generated power must be adapted before it can cross entire regions. This is where transformers come in. Step up transformers at power plants increase voltage to extremely high levels, sometimes hundreds of thousands of volts. Why so high? Because the higher the voltage, the lower the losses as heat in the wires during transmission. This is the grid's way of sending electricity far efficiently. Once voltage is stepped up, electricity enters the transmission network. These are the giant metal towers and thick cables you see stretching across long distances. Think of this part as the highway system for electricity. Its job is not to deliver power to individual homes. Its job is to move massive amounts of energy from where it is generated to where it will be used. Transmission lines form a large interconnected web. If one line fails, power can be rerouted through other paths to keep the system running. This interconnection makes the grid more resilient, but also more complex. A problem in one part of the grid can sometimes trigger chain reactions far away if the system is not carefully managed. As electricity approaches cities and towns, it passes through substations. Substations are the nerve centers of the grid. Inside a substation, voltage is stepped down from very high transmission levels to medium voltage levels suitable for neighborhoods and industrial zones. Substations also contain equipment that can disconnect parts of the grid during faults. This protects other sections from damage. From here, electricity is ready to enter the local distribution network. If this type of behind-the-scenes explanation interests, you make sure you are subscribed. Upcoming videos will explore how the internet, global logistics, and banking systems work in the same invisible way. After leaving the substation, electricity travels along smaller power lines that you often see along streets or buried underground. This is the distribution system. It is responsible for delivering power to homes, buildings, and small businesses. On poles or in metal boxes you might see in neighborhoods, there are more transformers. These step the voltage down again, from medium levels to the low voltages used inside buildings. From those transformers, cables run to your house or apartment building. They connect to your electrical panel, also called a breaker box. The panel divides power into different circuits around your home. Every outlet, every light, every device you use is connected back through these circuits, all the way to the distribution network, the substations, and ultimately to the original power plants. Most power grids use alternating current or AC instead of direct current. In AC systems, the direction of the current reverses many times per second. This choice was made because AC is easier to transform to higher or lower voltages. That makes it perfect for a system built around transformers, long distance transmission, and local distribution. But there is a catch. In an AC grid, many generators and consumers must operate in perfect synchrony, like instruments playing in the same tempo. If there is too much demand and not enough supply, frequency drops. If there is too much supply and not enough demand, frequency rises. Keeping this balance in real time is one of the main challenges of grid operation. The power grid has a unique problem. Electricity is mostly used at the exact same moment it is produced. Unlike water in a tank, you cannot easily store massive amounts of electricity at low cost. That means grid operators must constantly predict how much electricity people will use and adjust power plants accordingly. When people wake up, cook, work, and turn on air conditioners or heaters, demand rises and falls in predictable patterns. Control centers monitor the grid 24 hours a day using real-time data. They decide which power plants should produce more, which should reduce output, and how power should flow through the network. If this balance is not maintained, parts of the grid can become overloaded. In extreme cases, that can trigger protective shutdowns and cause blackouts. And most of the time, the grid appears stable and invisible to you, but when something goes wrong, the consequences are very visible. A major transmission line might fail because of storms, heat, or equipment problems. If other lines suddenly must carry more power than they were designed for, they may also fail, creating a domino effect. In some cases, a local fault can cascade into a regional blackout if protections and backup systems are not fast or strong enough. This is one reason why redundancy monitoring and planning are so important in grid design. Blackouts are not just inconvenient. They affect hospitals, communication systems, transportation, and entire economies. In recent years, more and more electricity has been coming from renewable sources like solar and wind. These sources are cleaner, but also more variable and less predictable. The sun does not always shine, and the wind does not always blow. This means the grid has to adapt to fluctuating generation on top of fluctuating demand. To handle this, modern grids are adding energy storage such as large battery systems and pumped hydro. They are also using smarter control systems that can rapidly adjust how power flows through the network. Some consumers are even becoming prosumers. They produce their own power with rooftop solar and feed excess energy back into the grid. This turns the grid from a one-way system into a much more dynamic two-way network. Electricity reaching your home is not guaranteed by nature. It exists because of infrastructure technology and constant human oversight. Every watt you use has traveled a long and carefully controlled journey, and the moment that journey breaks, modern life feels it immediately. If you want to keep understanding the systems that silently support your daily life, subscribe to the channel and turn on the notification bell. In the next video, we will reveal how the internet really works behind the scenes, how information leaves your phone, travels across oceans through cables and data centers, and somehow reaches another screen in milliseconds. If you want to see that explanation when it comes out, make sure you are following this channel and that the bell is on. That is how the world works.